class. Welcome to AP Calculus. Hope the college fair is going great.
Okay, let's start with your homework. Did you all check this already? Yeah. Okay, so if you did not check it, it's online. Check it now. So number 1 is continuous because all 3 pieces are equal. Number 2's not continuous because the left-hand and right-hand limit are not the same, so it's jumped. Number 3 is not continuous because I'm not defined it to. Did you see that? But my left-hand and right-hand limits are the same, so it's a removable whole. Number 4 is continuous at 2. Number 5 is not continuous, has a whole because my left and right-hand limits are equal, but my function value is not the same. 6 is clearly not continuous, but you could show that with a limit. 7 is continuous, and then 8, k equals 3 to make it continuous. Any questions on that? And then the back. Can someone, before I take questions, give me just a really, really basic, not a word for word from the video, but a basic definition of what the intermediate value theorem says? No one? Can you? Thank you. Go ahead, Ariana.
So what I have written down is that f is a function continuous and everything between A and B.
Uh-huh.
So between the points A and B, the function hits every point in there.
Good. So it's going to hit every x value. But then the important part about the intermediate value theorem, and I'm just going to pull up a new slide, is that if my function's continuous, I think a diagram is the easiest way to see this. If my function is continuous between A and B, let's call this f of A, because that's my function value in A, and this f of B. So if I draw through without lifting up my pencil, if I connect A to B and draw without lifting up my pencil, then what y values am I going to hit? Everything between f of A and f of B. I have to hit all of those y values. Do I have to hit this y value? Could I? Yeah, I could go down and then up, but I'm not guaranteed to hit it at least once. Does that make sense? But I am guaranteed, no matter what this function does, if it's continuous, to hit every value between f of A and f of B at least one time, maybe multiple times. Does that make sense? It's not a hard concept. But it has to be continuous. If I wasn't continuous, do you see that wouldn't be true? I could have a jump where I'd have a gap in those y values. But intermediate value theorem says that if your function's continuous, you're going to hit every y value between the y values of your 2 endpoints at least one time. So going through these, I just want to talk through them. So f is continuous from 0 to 2, and here are some values. If I say that my function has a y value of 1/2 at least 2 times, then what does this k value have to be? So if I start at 0, 1, at 0, 1, and then I have the point 2, 2. And I need it to hit 1/2 at least twice. If I go from 0, 1 to 1, 1/2, and then up to 2, 2, do I have to hit 1/2 twice? No, I could just hit it that one time and then go straight back up. Do you see that? But if I go from 1 to 0, do I have to pass through 1/2? Yeah, do you see that? So if I let this be 0, I have to pass through 1/2 to get to 0. And then if I go from a y value of 0 to a y value of 2, do I have to pass through 1/2? Yes. So that's why it's 0. If I let it be 1, if I let k be 1, if I go from a y value from 1 to 1, do I have to pass through 1/2? No, I could go straight across. Could I pass through 1/2? Yeah, I could go down and then back up, but I don't know for sure. If I go from 1 to 2, do I have to pass through 1/2? Could I? Yeah, I could go down and then back up, but I don't have to. And the same thing for each of the other ones. Does that make more sense? So if I let it be 0, to go from 1 to 0, I have to pass through a y value of 1/2, and then from 0 to 2, I have to pass through again. So that's why 0 is your solution. Does that make more sense on that one? Same thing here. Least number of solutions that my y value equals 1/2 on the interval from 1 to 8. So we can just sort of count. If I start at the point 1, -2, I'm starting at a y value of -2. As I go from -2 to 3, do I have to pass through 1/2?
Yes.
Yes. I have to hit every y value between -2 and 3. So I do pass through at least one time. If I go from 3 down to 1, do I have to pass through 1/2? No. Could I?
Yes.
Yeah, but I don't know. So I'm not guaranteed by the intermediate value theorem. If I go from 1 to -5, do I pass through 1/2?
Yes.
Yes, I'm guaranteed that I will pass through 1/2. Could I pass through 1/2 multiple times?
Yes.
But I don't know. I just know for sure that there's one time. And then between -5 and 7.
Yes.
So there definitely are 3 solutions, maybe more, because my function is continuous. This is completely conceptual. Like, you have to see it. There's no formula to follow. Does that help clear that up? Cool. And what has to be true about my function for the intermediate value theorem to hold? It has to be continuous. If it's not continuous, you can't answer any questions about the intermediate y values that you pass through. Way to go, Zach. Sounding smart. Sounding smart on the recording. Way to go. It's cold in here? Is that pertinent to these people that are watching online? Okay. Anything else you want to tell them about the environment?
Play outside, sliding through the trees, breathing slow.
I know they know more than we do. We're stuck in a prison. Okay, so today, our last new thing before your test on Thursday. So this is your last bit of new material, and then we'll review tomorrow and test on Thursday. Also, if you note on the board, if you have a lot of questions, I will be here from 3:30 to 4:30 on Wednesday, even though you don't have school. So you can come to school for that hour, and if you have any questions, I'm happy to answer them. Yes. So day 6, infinite limits. Before we even start, don't even look at that first limit. Actually, you can write it down if you want to. Yes.
What is your concept?
Take a guess.
Review.
Good job. Learning Spanish. What does RE mean? To do again. So that's like in a lot of languages it means to do again. What does like paso, what word can you find in there? Pass. So we're going to pass over stuff again. We're going to review it. So we're looking today at infinite limits. And I want to start by looking at the limit as x goes to 2 of 3 over x minus 2. Before, I don't even really want you to think about how to do this. I want you to go through the 4 ways we know how to evaluate limits. What's the first one? Direct substitution. Let's try that. What do we get? We get 3 over 0, which is what? Undefined. It's not indeterminate. It's not 0 over 0. It's undefined, which is different. Can we factor this? No. Can we rationalize? Can we least common denominator? No. And it's not even indeterminate. We just cannot simplify this in any way to make it look better. So what is the only way we know how to evaluate a limit if we can't do those things? What did we start with? Well, graphing. So we could actually graph this. But if we didn't know how to graph it, what could we do?
Plug in numbers.
Plug in numbers from either side and see what's happening. Does that make sense? So that's what I want to do to start with this limit. I want to make a table of values. So I'll give you a second to make a table. And then I'm going to have each of you plug in a different number, and we'll see what this limit is approaching. So Zach is going to get calculators, because yes, you can plug into your calculator for this. Way to go, Zach. So we cannot just substitute in 2. We get an undefined value. So what we can do is substitute in values that are approaching 2 from either side, from the left-hand side and from the right. So as you're getting your calculators, if Sadie's column will plug in 1.5, Catherine's column will plug in 1.9, Mary Hunter's column can plug in 1.99, and then I'm going to remember how to do this time. Connor's column is going to plug in 2.5, Logan's column is going to plug in 2.1, and then Brian's column is going to plug in 2.01. So substitute those values in, and let's see if we can figure out what our function values are approaching.
Two.
Olivia's going to plug in 2 over and over again and see what happens. Isn't it great that I have a perfect, like, 7? So 3 on it comes to Olivia. That's why Olivia's in a row by herself.
Yeah.
So I'm gonna approach from the left, so substitute in values. Sadie, what do you get when you substitute in 1.5?
-6.
-6. What do you get when you substitute in 1.9? Anyone?
-30.
-30. And what do you get when you plug in 1.99? -300. Doesn't look like we're approaching a single value as you go to the left. What's happening?
It's like
They're getting an absolute value bigger and bigger and bigger, more and more and more negative.
Yeah.
What happens when we plug in 2.5? We get 6, 2.1, and 2.01, 300. So am I approaching any one value?
You are approaching.
I'm definitely not approaching 0. What am I approaching? I'm just getting bigger and bigger and bigger. If I plugged in 2.00000001, what would my bottom practically be? 0. I get 3 divided by a tiny, tiny number, practically 0. 3 divided by practically 0 is what? What kind of number? A huge number, right? 3 divided by a number that's almost 0 is a huge number. If I plug in 1.9999999, what is this number practically? It's practically what? 1.9999999 minus 2. It's practically 0. But this time it's practically 0, but it's what? It's negative. You see that? So 3 divided by practically 0 is infinity, is going to infinity, but this time it's negative infinity because it's approaching from the other side. Does that make sense? So from this chart, we can see that the limit as x approaches to from the left, for numbers that are a little bit smaller, what is that approaching? Negative infinity. That equal sign is not a very good sign, but it's approaching negative infinity. And my limit as x goes to 2 from the right, so from values that are bigger than 2. What am I approaching? Positive infinity. And actually, I hope that you know what that graph looks like. What's my parent function? 1 over x. What does that 3 do? It stretches it, but for our sketch, we don't have to actually write that. But what is important is what does the plus 2 do?
It moves.
Good. So now I'm shifted over 2. As I approach 2, from the right, what's happening? I'm going to positive. Positive. So as I approach 2 from the right, I'm going up to positive infinity. And then we'll talk more about horizontal asymptotes. And as I approach 2 from the left, what's happening? negative infinity, and it goes like that. So we could have graphed that function already, but now we saw what those limits did by plugging in values. What is the limit as x goes to 2? What would we say about that?
It does not even.
Does not exist, because we have different left and right behavior. One's going to positive infinity, one's going to negative. Does that make sense? Let's do another one. 1 over x minus 1 squared. Oh, that's not really a limit. But we're going to take a look at this function. F of x equals 1 over x minus 1 squared. Someone asked me a boring limit. Like, I can ask you the limit as x goes to what? 0. Do you see that that's boring? What do you use? Direct substitution. Limit as x goes to 5. You can do that, just direct substitution. What's the one that you think that I want to do? At 1. I want to figure out what's going on as x goes to 1. If I do direct substitution, if I use direct substitution, what do I get? 1 over 0. What is that? Undefined. And I'll tell you now that means it's either going to positive infinity or negative infinity. Because 1 divided by a really, 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 really small number, getting closer and closer to 0, is just getting bigger and bigger and bigger. Does that make sense? You can try it with your calculator. If you do 1 divided by 0.00000001, it's huge. And you can make it get as big as you want by getting as close to 0 as you want. But I do need to figure out if it's positive or negative infinity. So I'm going to look at the limit as x goes to 1. You want to do from the left or the right first? Left. I'm going to write out the function. So 1 over x minus 1 squared. If I plug in something smaller than 1, someone give me something smaller than 1, but closer to 1.
0.9.
I would do 0.9. I usually like to be within a 10. So if I plug in 0.9 or 0.99, do you see that this is practically 0?
Yes.
Is it positive or negative? But then I square it. So what does it become?
Positive.
Positive. So 1 divided by practically 0 and positive. What's that going to? Positive or negative? Positive. Does that make sense? 1 divided by a tiny, 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 tiny positive number is going to positive infinity. And if I look from the right, if I plug in 1.1 or 1.01, 1.1 minus 1 or 1.01 minus 1, it's going to 0, and it's a positive or negative? Positive, and I square it, still positive. So this is 1 divided by practically 0 and positive. It's going to positive infinity as well. So these ones are both going to infinity. Do you see how we're doing this numerically? We're plugging in values close to 0, but we don't actually have to see what they equal. We just know they're getting really big. So both of those limits are going to infinity. If I were to graph this, we don't even have to graph the whole thing. At 1, as I approach 1 from the left, what's happening?
It's getting bigger.
It's getting really, really big. As I approach 1 from the right, what's happening?
It's getting bigger.
And nothing happens at 1. At 1, I'm undefined. What do you see happening there? Mass. So can you see that asymptote being created?
Yes, ma'am.
So try this one. This function. What limit do you think I'm interested in? 3. And I want to look at the limit as x goes to 3 from the left and the limit as x goes to 3. So with your partner, see if you can figure out what's happening at 3.
Alright.
But it's like, so from the left, you have to get here. From the right, you have to get here.
Doesn't that give you like a big,
Big, big.
like, negative R, negative 100, negative little.
And since I want to do it out loud clear, I want you to think about it conceptually. So don't actually substitute values. Yes.
I was like, I'm working in discussion about biology stuff, and I was like, I'm gonna calculate, and I was like, I'm just starting to like.
It's so fun. It's the most satisfying course you'll ever see. Okay, so what happens when we use direct substitution? What do you get? Undefined, which tells you that it's going to be what or what? Positive infinity or negative infinity, and you just have to figure out which one. Does that make sense? Because you're taking a number 1 that's fixed and letting the bottom get really, really small, which just makes your fraction get huge. We just have to figure out if it's positive or negative. And that depends on what side you're approaching it from. So if we plug in something smaller than 3, like 2.99, you see the bottom's getting closer to 0. This fraction's getting big, but what's important is my bottom negative or positive? Negative. From the left, it's negative. Is my top negative or positive?
It's negative.
So what's it approaching?
Positive.
Positive infinity. And then from the right, if I plug in values like 3.01, my bottom's getting closer to 0. And is it positive or negative?
It's negative. Well, it's the bottom's
The bottom's positive. So negative 1 over positive 0,
negative.
negative infinity. Does that make sense? If I were to graph this function, you should already know what this looks like. But if you didn't, let's get a really good graph of this. What's happening at 3? There's an asymptote. If I approach 3 from the left, I'm going up to positive infinity. As I approach 3 from the right, I'm going down to negative infinity. And we'll talk again later. Actually, no, let's talk about it now. If I wanted to do a really good job graphing this function, where is my, well, this is just a good question in general. What is my y-intercept? How do you find y-intercepts? Plug in 0 for x. So what's my y-intercept? 1/3. So I know I cross at the point 0, 1/3. What's my x-intercept?
There isn't one.
There isn't one. If I set this equal to 0, my numerator never equals 0. So I know it never crosses, which means that I'm going to cross through this point, but I can never cross. So I've got an asymptote here, and I come up, and that's what my function looks like with my intercepts. Could you have graphed that without doing these limits? Shifting over 3 in a reflection, but we can also see it with the limits by substituting in those values. So we've been throwing around a word that we're going to define right now, a vertical asymptote. And the formal definition of a vertical asymptote is if the limit as x goes to a from the right of f of x equals positive or negative infinity, or if the limit as x goes to a from the left equals positive or negative infinity. So as I approach a from the right, if I'm going up to positive infinity or down to negative infinity, or if I approach from the left, I'm going up to infinity or down to negative infinity, then what is happening at a? There's a vertical asymptote. This, the vertical line x equals a, is a vertical asymptote. Hold on 1 second. And I'll take your question. One thing that's important to note is that vertical asymptotes, I usually abbreviate them, occur when the denominator equals 0, but the numerator does not. What happens if both your numerator and denominator are 0? It's indeterminate, and then you can usually factor or rationalize or find a least common denominator, and there's probably a hole there. But if your numerator equals not 0, but your denominator does equal 0, that's where you have a vertical asymptote. Because your bottom's getting closer and closer to 0, but your top's not getting closer to 0. So you're just getting a very, very, very large number. Yes, you suppose your question.
So you say, or if going from x approaches
Yeah.
is negative 3. Is there ever a case where only one side is approaching infinity and the other side is not?
A piecewise function, maybe.
Yeah.
So they're two different pieces, but a regular like function with one rule, I cannot think of a time where it wouldn't be.
So would you say that you said something like there is a vertical asymptote?
Yeah, so like if you have a piecewise function, let me draw one up here. Say, I'm not going to write out the piecewise function, but you could definitely have a piecewise function that looks like that. That's a vertical asymptote, even though it's defined on the other side on your asymptote. That's not very common that you see, but yes, that's a vertical asymptote. Good question. So, for example, I want to find any vertical asymptotes on this function and then write it as a limit. We said, sorry, I'll let you write that out. Do you like having the presentation, or do you wish that I was writing with you?
I like it.
It's both.
Yeah, you can find both.
I don't understand that.
I don't know. Both.
I like writing with you because right now I like want to move ahead, but you all have to write this down. Also, I write a lot neater on paper than I do on smartboard. Okay, so vertical asymptotes occur where what equals 0? The denominator. When you're dividing by 0, but your top isn't 0. And so to find my vertical asymptote, all I have to do is set my denominator equal to 0. What does x equal?
-1.
So x equals -1 is a vertical asymptote. I want to describe it in terms of limits, so figure out if I'm going positive or negative infinity from which direction. So how many limits am I going to need to do? 2. I'm going to need to look at the limit as x goes to -1 from the left. And I'm going to need to look at the limit as x goes to -1 from the right. So on your test on Thursday, I will ask you to write a vertical asymptote as a limit, and so you have to get the right positive or negative infinity. And the way we do that is numerically, is by substituting in values and thinking in our head, is this positive or negative? So I'll do this one with you. -1 from the left. This is hard with negatives. What kind of values am I substituting in? -1.1. Yeah. So just a little bit, think of a number line, and then go a little bit to the left of -1. Does that make sense?
So wait,
Yes.
so it's kind of like backwards almost.
-1.1 is smaller than -1. Yes.
Yes.
-2 is smaller is a bad word. -1 is farther to the left on your number line than -0.5. So we want to go from the left. So negative 1.1. Negative 1.1 plus 1 is a positive or negative.
Negative.
So 1 over a negative number is left.
Negative.
That one's going to negative infinity. So as I approach negative 1 from the left, I'm going down to negative infinity. Negative 1 from the right. What's a value that's just to the right of negative 1?
Negative 0.9.
Negative 0.9. Negative 0.9 plus 1, positive or negative?
Positive.
Positive. So 1 divided by a positive 0.
Positive.
Positive. And so that's how I prove that that's a vertical asymptote, because as I approach 1, I'm going to positive or negative infinity. Now we're going to take it a step further. It's going to be okay, Logan. Does your knee hurt, or does calculus hurt?
My knee hurts.
How was your-
What happened to your knee?
Oh, I just did not. But I
You got a break.
located it off.
Where did you start with that?
Why did your knee hurt? Because I hit it on the head.
Because I think it was, oh,
Is that, what's that mean?
Right. Taekwondo,
Mm.
fighting, but you're fighting an opposing
Uh-huh.
point, so I got hit.
Did you win?
We were doing 2-on-1, so they don't really score the points, but
Were you on the 2 or the 1?
we switched around.
Why did your knee go?
What were you on? Just
Okay, we're gonna do this problem. Fine, I gave you time to write it down, yes? I wanna find, what's very about is I wanna find holes and vertical asymptotes. So if I want to find, when do holes happen? First of all, actually, let's just stop. Where is this function undefined? Yes.
Plus or minus 2.
Plus or minus 2, because my denominator equals 0. Are both of those vertical asymptotes?
No.
No, because if I substitute in negative 2, do you see that my top and bottom are 0? So that's not a vertical asymptote. That is usually a hole. So before I even get started, when you see this function, what do you want to do?
Factor.
Yeah, I want a factor. And so I'm going to simplify this function. And see that this function actually looks like 1 over x minus 2. Everywhere except at what point? When x equals negative 2, because that also is not in my domain. And so what does happen at negative 2? There's not an asymptote. There's a hole. So that's what we did last week, is we factored it out and said, we have a hole. We removed the discontinuity at negative 2. We have a removable discontinuity at negative 2. No, negative 2, because that's what makes it 0 over 0.
But it can be 0 on the bottom.
That's an asymptote. We're going to get to there.
Okay.
Does that make sense? So we need to look at our limits as we go to 2 and negative 2. But here, negative 2 was making it 0 over 0, but we factored that out, so that's our hole. How do I find the y value of that hole? How do I find what it's approaching? Yeah, so I can take the limit as x goes to negative 2 of that function, which I've simplified into this, right? And so what am I approaching?
1 over 4, 1 over negative 4.
Negative 1/4. So I know that as I approach negative 2, there's no point there, but am I approaching the same thing on the other side?
Yes.
I'm approaching negative 1/4. So I have a hole at negative 2, negative 1/4. That's my removable discontinuity. I have a hole there. I was able, do you see how I literally removed it from my function? I took it out, but it's still there. Still, there's not a point there. Now, however, I have another discontinuity. What discontinuity do I have? I have a vertical asymptote. At what other point? X equals 2. Do you see how I couldn't remove that one? It's still making my denominator 0. And if I want to look at that, I can look at the limit as x goes to 2 But this time I have to go from the left and from the right when I'm writing that as a limit. So I'm going to look at the limit as x goes to 2 from the left. And I'm going to look at the limit as x goes to 2 from the right. I know they're going to infinity or negative infinity, but I need to figure out if it's going to positive or negative. So 2 from the left.
Negative.
Should we substitute into this or to that?
That.
That 1 over x minus 2 is going to be easier to substitute into and think about. So 2 from the left, I'm going to substitute in 1.99. Positive or negative on the bottom?
Negative.
Negative 1 over negative is negative infinity. 2 from the right, I'm going to substitute in 2.1 minus 2. Positive or negative?
Positive.
Positive, so I'm going to positive. And so now I can describe all of my discontinuities. I've got a hole at the point -2, -1/4, and I have a vertical asymptote at the point, or at x equals 2. On your test, I am going to challenge you to use that information to sketch a really accurate graph of that function. Was that Joy?
Yes.
Okay, I thought so. So let's practice on this one. What things do you know? I mean, it's pretty easy. You know you have a hole where?
Negative 2.
-2, -1/4. So I know there's a hole right there. What else do you know? There's a vertical asymptote at 2. So I'm putting those things together. Before I start thinking again, I want to look at intercepts. What's easiest, x or y intercepts? I think y is easier. You just plug in 0. What's my y intercept? Yeah, so now I'm going to cross. That's -1/4, so a little bit below it, -1/2. Do I have any x intercepts? So I'm going to look at my simplified function. Is that ever going to equal 0? The top? No. Does the top equal 0 over here? Yeah, but that's where my hole is. And so it's not even a hole on the x-axis. It's just like, it makes it, that indeterminate form makes it difficult to see where that is. So I don't have any x-intercepts. I know as I approach 2 from the left, I'm going down to negative infinity. And as I approach 2 from the right, I'm going up to positive infinity. And I do not cross the x-axis. Can you sketch in the rest of that graph? I can't touch the x-axis, so that's going to have I can't touch the x-axis, so that's going to have to go out like that. And here, I know I go through my y-intercept, approach my hole, but I can't touch the x-axis. That's a pretty accurate sketch of that graph. How do you feel? I want you on this to find any vertical asymptotes or holes. Write them as limits, and then try to. I'm going to give you 5 minutes on this. Yay, that's a lot of minutes. So I want you to try to find any vertical asymptotes and or holes. I want you to write your vertical asymptotes as limits. So you see which direction they're going in. Use that information to sketch a graph. Also think about intercepts. Yes.
0 over 0, that's when it's a hole.
Yes.
A number over 0, that's when it's a hole.
What should you do first? Like factor?
Yeah, factor.
Yeah. So you should factor and simplify your function, right? Is something going to simplify? When you can simplify that point, what was created there?
A hole.
A hole. You removed that discontinuity. So there's a hole where you can actually simplify your function. And then whatever's left over are vertical asymptotes.
This is a fun looking graph.
It is. And this is not a parent function. but we can use our limits as intercepts and holes to get a pretty good sketch of it. This is harder than what I've asked you to do before. As you're working, just make sure you're on track. How many vertical asymptotes do you have? 2. Which means how many limits do you need to check? 4 from the left and the right of both of them. When you're substituting back in to see if it's positive or negative infinity, where does your x go? Like where do you plug in? Sorry. To all of the x's. So you still have 2 and you need to check both of them. All you care about is positive versus negative. So for your hole, it's definitely at 4. And then how do you figure out the limits we approach? Yeah, that should be right. We did it. Oh, yeah, your hole. No, your hole is at 4. Because that's what makes it 0 over 0. So 2 over. Oh, then you're. Oh, man. Yeah, you're right. My original problem, that should have been -2, but this is fine. Now I gotta do this with equals I did it all the time.
Miss Allen,
Mhm.
the hole, is it what makes it 0 or is it what, like, so for this one, you said it was -2 because that's what this was earlier.
No, we said it because that's what makes it 0 over 0. Does that make sense? And then 2 was the asymptote, because that's what makes the bottom 0.
So it's what makes it 0 over 0.
Right. So we know that we're discontinuous at 4, 3, and -2. Does that make sense? Because that's what makes our bottom 0. But we can get rid of the x minus 4 over x minus 4. So that place 4, that's actually full. But 3 and -2 are for positive. It's not pretty scrappy, it looks great. I mean, except you don't actually put your whole like it. Or your whole. Makes sense.
That's just an artistic word, saying.
A horizontal or vertical? There's definitely a vertical. You can't have a horizontal pass and go to the next vertical. If. Well. So as you approach -2. So let's plug in. If you plug it in -2.00000001, if you plug it into your simplified function, it's going to be yeah, we can't plug it. It should still work if you plug it into your. If you plug in -1, -2. Can I store so maybe -2.0001 store that for x? So x equals that. And so by let's divide. Let's start going over this. What should I do? So where is my function discontinuous? What x values? 4 and no, like what x values are not in my domain? 4 and 3 and -2. Do you see that? They're not in my domain. They make my denominator 0. But not all of them are asymptotes because I can remove one of them. Yeah, so if I factor this into 2 times x minus 4, this simplifies into 2 over x minus 3 times x plus 2. Everyone good with that? Except, that's true except when x is 4, because 4 is not in my domain. So because I got rid of the discontinuity at 4, I know that I have a hole at x equals 4. And how do I actually find out what I'm approaching as I go to 4?
You put the limit as x equals 4.
I look at the limit as x goes to 4. I can plug it in here because that's already factored and simplified. And so I know that my hole is at 4 and it goes to 1/3. So that's where my hole is. My limit as x goes to 4 equals 1/3 of this function. We're good with that. Where do I have vertical asymptotes?
3 and -2.
X equals 3 and x equals -2 because I cannot remove them. They are in my function. I cannot simplify it anymore. So now I need to check 4 limits. Limit as x goes to 3 from the left. Limit as x goes to 3 from the right. Limit as x goes to -2 from the left. And limit as x goes to -2 from the right. And so this just takes a lot of time, but it's not hard. You just have to keep track. Should I substitute values into my simplified function or my original? It doesn't matter, but simplified is going to be easier. So what's the number a little smaller than 3 with? 2.9. 2.9 minus 3, positive or negative? 2.9 plus 2, positive or negative? Negative, positive, what's the bottom? Negative and practically 0, because it's getting closer to being 3 minus 3. So bottom's negative, top's positive, that's going to negative infinity. We're good with that? It's a lot of work, but it's not hard. 3.1, positive, 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 that's going to positive infinity. What's a little bit to the left of -2? Negative 2.1. Negative 2.1 minus 3 is still negative. Negative 2.1 plus 2 is also negative. So it's positive overall. Positive over positive. I'm going to positive. I'm substituting into both of these x's. And then a little bit to the right of -2 is negative 1.9. Negative 1.9 minus 3 is negative. Negative 1.9 plus 2 is positive. So it's what overall? Negative. And so now comes the challenging part, is I'm going to use all of that information to try to get a really good sketch of this function. I know that I have, I'm not going to worry about y values that much. I know that I have a hole at 4 1/3, so really close to 0. I know I have asymptotes where?
3 and -2.
3 and -2. Before I start sketching, I want to plot any other points. What are good points to plot?
Y-intercept.
Y-intercept and x-intercept. What is my y-intercept? So I plug in 0 for x. I get 2 over -6. So negative 1/3. Is that right? So my y-intercept is 0, negative 1/3. Does my simplified function ever equal 0? No, so I don't have any x-intercepts. I cannot cross the x-axis. And so using that, I know lastly that if I look at 3 from the left is going to negative infinity, and 3 from the right is going to positive infinity. I'm going to connect through that hole I can't cross. Now I'm going to look at my -2. -2 from the left is going to infinity. -2 from the right is going to positive infinity. I know I go through this y-intercept and I can't cross, so it's going to look like that. And I can't cross this. So I've got intercepts, holes, asymptotes, and directions that they're going. That's about as good of a sketch as I need. I want to see holes and asymptotes and directions that your asymptotes are going. How do you feel? Anyone graph this on their calculator to check?
No.
Oh, well, if you do, it'll look like that. I'm not going to do it because we have a lot to do today. Oh man. Finding any holes or vertical asymptotes of cosine x over sine x. So, holes happen where I can simplify my function. Does cosine x over sine x simplify? Cotangent. But it doesn't divide anything out. That's just a different way to write it. So nothing cancels out between cosine x and sine x. But I know that vertical asymptotes occur when what equals 0?
The bottom.
The bottom. So my vertical, I'm going to have a vertical asymptote anytime sine equals 0. When does sine of x equal 0? 0. If we look at our unit circle, at 0, and then again at where? Pi, and then again at 2 pi, and then again at 3 pi, and at negative pi. So, yeah, we can even say pi 0 plus or minus pi n, where n is an integer. So I have an infinite number of vertical asymptotes. It's wherever any multiple of pi. 1 pi, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi, negative 3 pi. Any integer times pi.
Wait, but doesn't that exponent wait? Forget it.
Okay.
What is the, like, what do you use to think that it's like plus or minus?
So you could really, sorry to interrupt you, that's a good question. You could really write 0 plus or minus pi n, but I don't really need to do the 0. And also, I think that I sort of made a mistake in making you do plus or minus, because integers can be negative, which is what picks up the minus. And if you put that, it's redundant. But I'm fine with that, 0 plus or minus pi n, where it's an integer, or just plus or minus pi n, where it's an integer. So cotangent, we said this is actually a cotangent. You remember what the graph of cotangent looks like? Yeah, it looks like tangent, but it's like flipped. How many vertical asymptotes does it have?
Infinite.
Infinite, every pi. That's where you have them, where your denominator equals 0 and you can't simplify. Sorry that today's a really long day. We're like 2/3 of the way done. Some quick properties of infinite limits. We're going to start with two scenarios. If the limit as x goes to c of f of x is going to infinity, and the limit as x goes to c of g of x equals f. Those are sort of our hypotheses. I don't know if they're called hypotheses. If these things are true, then we're going to figure out what else is true. So do you see that the limit as x goes to c of f of x does not exist? It's just getting bigger and bigger and bigger. But the limit as x goes to c of g of x does exist. It's approaching some value L. What do you think happens if I add those functions together? What's the limit as x goes to c of f of x approaching? Infinity. What's g of x approaching? So what are they approaching if you add them together? Infinity plus L, which is just what? Infinity. If one of your limits is going to infinity, then adding on another limit is still going to infinity, as long as that's finite. Does that make sense? I feel like your neck just started hurting, Logan.
I don't know what happened.
Okay. I'm scared that you're falling apart. Does that make sense? If one's going to infinity, it doesn't matter what the other one's doing, if it's just approaching some number. What happens if this one's going to infinity and that one's going to negative infinity? Sometimes, but sometimes they don't. That's an indeterminate form. We have to do some work to figure out what's going on. We'll get more of that later. If I multiply them together, f of x is approaching infinity, g of x is approaching L. What does that equal? Infinity, if what's true? L is positive. Good. So not your function, but your limit. So this goes to infinity as long as L is positive. And really, we should just kind of addend them onto. Limit as x goes to c of f of x times g of x. It's going to go not to infinity, but to negative infinity if what? L is less than 0. What happens if L equals 0?
All zero times zero.
Indeterminate.
Indeterminate. Infinity times 0 is indeterminate. We'll talk more about that later. That's another indeterminate form. It really depends on which one is. If it's growing faster, then it's approaching 0. But we will talk a lot more about that in a few weeks. It's really cool stuff. And then this is a really important one. Limit as x goes to c of g of x divided by f of x. What's g of x approaching? Some number L. What's f of x approaching? So if I have some number L, like say it's 5, and the bottom just keeps getting bigger and bigger and bigger and bigger.
You're getting smaller, smaller, smaller.
It wouldn't be negative infinity. So 5 divided by 1 billion is really close to what?
Zero.
0.
Zero.
So if my bottom's getting really big, but my numerator is not growing, I'm approaching 0. Does that make sense? If you divide by a huge number, your fraction is tiny. It's getting closer and closer to 0. So for example, just a quick example of that. Limit as x goes to 0 of 1 plus 1 over x squared. What's the limit as x goes to 0 of 1?
1.
It's just 1. It's a constant 1. What's the limit as x goes to 0 of 1 over x squared? It's infinity, because the bottom is always positive and approaching 0, and 1 divided by practically 0 is going to infinity. So this is going to 1. This piece is going to 1. This piece is going to infinity. So what's it going to overall? Infinity. The 1 doesn't matter. How are you feeling? Good. Tired?
I'm pretty tired too.
Why didn't you go to sleep last night? We've only been in school for 3 weeks. Okay, so this is sort of the pause of vertical asymptotes. What other types of asymptotes do we have? Horizontal. And this is horizontal asymptotes. I promise you have done before in pre-calc, and they're really easy. So we're going to go over them quickly. Horizontal asymptotes happen as x approaches infinity or negative infinity. So instead of looking at what's happening as x approaches a certain value, we're looking what happens as x gets really, really big towards the positive infinity side or really, really big at negative. Does that make sense? We're saying, do we level out eventually? So when I talk about end behavior, I'm looking for horizontal asymptotes. And it's what happens as x approaches infinity or negative infinity. And so we're going to start by looking at two functions. Y equals e to the x and y equals x. Do you know what y equals e to the x looks like? I hope. Good. Exponential function. It starts out, it's always positive, but it starts out growing slowly, and then it grows faster and faster and faster. There's y equals e to the x. What does y equals x look like? It's just a line. What kind of line? Oh, a lot of lines are diagonal.
Linear.
With the slope of 1.
Slope of 1 goes through what?
0. That's the point
The
of
origin.
1, 2, 3, 4, 4.
Yes. So y equals x. What question do I want to ask? As x gets bigger and bigger, what are my y values doing on e to the x? They're getting bigger and bigger. Where are they going? To positive infinity. What happens on my function y equals x as x gets bigger and bigger? Also going to positive infinity. Which one's going faster? E to the x. You can see that it gets steeper and steeper. Y equals x is also going to infinity, but it's taking its time. It's going over 1, up 1, over 1, up 1. E to the x gets faster and faster and faster. Does that make sense? So when we're looking at horizontal asymptotes or limits as x goes to infinity, we can think of it as a race comparing the numerator to the denominator. Which one's going to infinity faster? And so, if we look at the limit as x goes to infinity of e to the x over x, what's my top going to? What's e to the x going to? Infinity. What's the bottom going to? They're both going to infinity. But which one's going faster? E to the x. So my top is getting really, really big. And my bottom is getting really, really big, but not as fast. Does that make sense? So the difference between them keeps growing and growing and growing. My fraction keeps getting bigger on the top more than it gets bigger on the bottom. So what is that going to go to? What do you say, Olivia? Positive infinity. My top is growing faster. That fraction just keeps growing. Both the numerator and denominator are getting bigger, but the top is getting bigger faster and faster and faster. If we look at this, do you see that at x over e to the x, do you see that x is going to infinity? And e to the x is going to infinity. But which one's growing faster? E to the x. So if I have the difference between them keeps getting bigger. My bottom is getting way bigger than the top. So what's this going to?
Zero.
0. It's a smaller number divided by a bigger number, and that is approaching 0. You have done this before, and now we're just going to put limits on it. So we're going to do so many examples really, really fast. Are you still nervous?
Yeah.
Well, we're about to go fast, so get tired. We're going to look at the limit as x goes to infinity of 1 over x. What's the top going? Which one's bigger, the top or the bottom? The bottom. The bottom's getting huge, and the top is just staying at 1. So as we plug in 10 and 100 and 1,000 and 1,000,000, what's it getting closer and closer to? So the bottom is bigger. So that limit is just equal to 0.
Stay with it. Stay future with it.
Limit as x goes to infinity of 2x cubed plus 5 over 3x squared plus 1. Both of these, what's my numerator going to?
Infinity.
Infinity. What's my denominator going to?
Infinity.
They're both going to infinity. But which one's going faster? The numerator, because you're cubing it instead of just squaring whatever number you're plugging in. So when you get x to bigger and bigger values, it makes more and more of a difference. So what's this going to? Infinity. Yep. Limit of x goes to infinity of 2x minus 1 over x plus 1. What's my numerator going to? Infinity. What's my denominator going to? Which one is going faster? The top. How much faster?
2x.
It is going twice as fast. We can actually measure how much faster it's growing. And so, I want you to imagine plugging in 1,000. If we plug in 1,000, that's going to be practically 2,000 on top and 1,000 on the bottom. You see that? So it's approaching 2. And the farther out we get, the closer it actually just approaches 2. So this is not going to infinity even though the top's bigger. It's just approaching a fraction that's closer and closer to 2. Does that make sense? If you, because this is cubing and squaring, it just gets bigger and bigger and bigger. The top on number 3 is bigger than the bottom, but it's approaching to be exactly twice as big, which is just a fraction that simplifies. If we look at the limit as x goes to infinity of 4x cubed plus 2x plus 7 over 5x cubed plus 9. They're both going to infinity. They're both getting really, really big, the numerator and the denominator. Which one's going faster? The denominator, but it's at a rate that we can sort of understand. It's at a rate, a comparison that we can understand. We're cubing both of the x's, but we're multiplying the top by 4 and the bottom by 5. Do you see how when x gets really, really big, all this stuff isn't going to matter compared to what's happening to the cubing? So we can sort of forget about that and say that as we go way out for x really, really big, what's this going to approach? 4/5. So that limit just equals 4/5. And I will show you another day. But if you put that function into your calculator and substituted really big values for x, your fraction just gets closer and closer to 4/5. Does this look familiar to you? So you probably learned horizontal asymptote rules in pre-calc. If you have the same degree, meaning power on my exponent, in your numerator, this is numerator, and denominator, what do you do? What do you look at to see what it's approaching? It's gonna be a phrase that should bring back. Look at the ratio of your leading coefficients. Does that ring a bell? So look at ratio of leading coefficients. And that's what we did for 3 and 4. It was a linear function in the top and bottom for 3. So we just looked at the ratio of leading coefficients. It was a linear, or sorry, they were both cubic and number 4. So we looked at the ratio. A few more. Look at the limit as x goes to infinity of 2x cubed plus 4x to the 4th over 3x cubed. What is that going to? What's bigger, the top or the bottom, or are they the same degree? The top is bigger. You have to look at which exponent is bigger. We've got a 4 on top and a 3 on the bottom, which means that this is going to what? What if I took that same problem and changed it to that? Now what's bigger, the top or the bottom? Which one is growing faster? The top is still growing faster, but if you substituted in 1,000,000, your numerator would be negative, and your denominator would be positive. So what's this going to? Negative. What if I let x go to negative? So instead of looking on the right side of my graph, I'm looking on the left side of my graph.
Good morning. I need Dallin Andrew to the front office for checkout.
He's at the college fair. On this one, limit as x goes to negative infinity. What's growing faster, the top or the bottom?
The top.
The top is a higher degree on top, but if I plug in really big negative numbers for x, is my top positive or negative?
Negative.
And my bottom positive or negative?
Positive.
Positive. So what's it going to go to? Negative infinity, because my top's negative and my bottom's positive. And my last one. Limit as x goes to negative infinity of 3x squared plus 1 over 2x cubed plus 5. What's bigger, the top or the bottom? The bottom. Which means if my bottom's bigger, what's that fraction going to?
0.
0. Positive or negative 0?
Positive.
It doesn't matter. It's going to 0. And maybe I could look and see that it's approaching 0 from numbers that are less than 0, but that limit is approaching 0. 2 quick things to formalize. All of those. When we look at what my function is approaching as x goes to positive infinity or as x goes to negative infinity, we're looking at horizontal asymptotes. So what's my function leveling out to on either end? So the definition of a horizontal asymptote says if the limit as x goes to infinity of f of x equals b, or if the limit as x goes to negative infinity, so on either side, if that equals b, then we say y equals b is a horizontal asymptote. You can have 2 different horizontal asymptotes. So for example, if you have a graph that looks like that, they could be approaching different things on the left and the right. And so for horizontal asymptotes, we're looking at that end behavior as we go out on either side of our graph. So if I asked you, these are really easy. We have an example on one for you to try, and I'm done. I know it's been a long day. So if we want to find horizontal asymptotes of this function, 2x squared over x cubed plus 8, then what should we look at? Yeah, as x gets really, really big, are my y values going to level out? So I'm going to look at the limit as x goes to infinity of 2x squared over x cubed plus 8. What's bigger, the top or the bottom? So what is this going to?
0.
Therefore, because that limit is going to 0, what is my horizontal asymptote?
Y equals 0.
Yeah, y equals 0 is your horizontal asymptote. Find the horizontal asymptote and write it as a limit here. I'm going to look as x gets really, really big, is my function going to level out at any specific y value? Does that limit exist? What is it? So therefore what? Y equals -2 is your horizontal asymptote on x. What would happen if that became a 2x to the, or sorry, -4x to the 4th on top? It would go to -infinity. Good. So, which means that as x goes to infinity, I'm going down to -infinity. What's my horizontal asymptote? I don't have one. I'm just getting smaller and smaller and smaller. I'm not leveling out to any specific y value. How do you feel? Tired? I know today was really long, but I feel that it's good to get through it so that we're done with new stuff for your test on Thursday. Your homework tonight is section 1.5, and then we're jumping to section 3.5 because horizontal asymptotes, they don't do till chapter 3, which I think is dumb.
What?
Is your mom gonna watch this?
No, I'm saying that.
Okay.
I feel like I'm like.
I feel like shout outs are usually so the other person can hear you shouting. But you do you, Greg.
Shout out to Dallin.
Dallin already got a shout out from the front
Shout
office.
out other seniors. I hate
Tommy Allegro, big news.
Looking ahead, so there's your homework for tonight. Come tomorrow with questions. I'll have some practice problems for you to do tomorrow. And then because you have a day off, I have some extra problems that you can do on Wednesday if you want to, and I will be here. I'll post answers so you can check them. And I will be here after school today, tomorrow, and Wednesday. So feel free.
Will you be here before school on Thursday? So how can people apply?
Does it say that? I will be, yes.
Shout out to the,
Yes.
I
shout
can't
out to Lydia.
Shout out to who?
You, Lydia Allen.
Everyone say goodbye.
Bye.